Hello, Chem 1B. This is Chapter 17, Lecture Video 5. We're now going to start talking about acid-base titrations involving something weak with something strong. Now, there are only really three types of acid-base titrations we'll be covering in this class, and that is a strong acid and strong base titration, right, when both things are strong. And then the other two are when the base is weak and we're titrating with a strong acid, and finally when the acid's weak and we're titrating with a strong base. Now, I actually am only going to be able to cover, just due to timing, this guy, but it's pretty much the reverse for the weak acid strong base titration, and I have slides up for that in Canvas. I just don't have a video for it, so if you go through those slides, you can always ask me questions about them in the discussion sessions, and I'm happy to go over anything in there. All right, so let's say we have some weak base, we'll call it A-, and it's reacting with HCl, a strong acid. Before any acid is added, the solution initially contains only the weak base, and therefore our pH is pretty much just given by an ice table, icebox calculation. We can use the weak base to calculate the OH- concentration. This will allow us to get the pOH, then get the pH from there. So if we're doing this part of our pH curve when we do a weak base with a strong acid, and we're going to be building this curve over the next couple lecture videos probably. The initial point, that's just an ice table calculation. This is something we learned how to do in chapter 15, right? So let's say we do an example of that, right? What is the initial pH for a titration of, 25.0 milliliters of 0.126 molar ammonia, a weak base, with 0.287 molar HCl. Now, technically, we really don't care about this guy because it's the initial pH, meaning we haven't added any HCl yet. So effectively, all I have is NH3 in water, and I know that that's a weak base, so it breaks up into all this, right? And this is my equilibrium. I have to write out my ice table as a Kb, right? Equilibrium, and we're given the Kb of NH3. So I know that I have 0.126 molar here initially. And I don't care about water because it's pure liquid. These two are 0 initially. And my change is going to be minus x plus x plus x, x, 0.126 minus x. And I can set all this equal to the Kb, right? 1.8 times 10 to the negative 5 is equal to x squared all over 0.126 minus x. I am definitely going to use the 5% rule here and just kind of simplify my answer here. This way I can now solve for x, and that gives me 0.00151 molar is my x value. Now x is equal to OH-. So if I take the negative log of that guy, I get pOH, is equal to, negative log of 0.00151. This is equal to 2.82. Now my pH is 14 minus that, so if I do that calculation, I get that pH is going to be equal to 11.18, I guess, technically, rounding wise, 11.18. Now hopefully this makes sense because we have the initial pH, right? All we have is weak base in the solution, so we should definitely be expecting a weak base to have a pH of above 7, which is what we have here. So cool. Let's look at the next area of our titration curve, where once we start adding strong acid, it's going to start consuming some of the weak base because, acids react with bases. This is going to convert the weak base, at least a small amount of it, to its conjugate acid. In other words, we're making a buffer in solution. Now, that neutralization step, as always, is a non-equilibrium step. This is a neutralization, and it goes to completion. Some of this goes down, this comes up. we have a buffer at the end of this, as long as this is the limiting reactant, right? It occurs instantaneously, and we can say it goes to completion, meaning no equilibrium is involved. So what's left in solution? We have both HA and A minus present. This means we have a buffer. So after the neutralization reaction is complete, an equilibrium is going to exist between both the weak acid and its conjugate base. And since we have a buffer, we can use Henderson-Hasselbalch to solve the problem. So again, this is a two-step process. Once we've actually started to add acid to the system, we need to first do the neutralization step, figure out how much weak base is left, how much weak conjugate acid was formed, and then we can plug in to the Henderson-Hasselbalch equation to solve for the pH of the solution at this point in the titration. Now, this is what we call the buffer region of the titration curve, because we have a buffer present, and we can use Henderson-Hasselbalch. So, one of the things you should also know is that as we know, pH is equal to pKa when both HA and A minus are equal to each other. Now, that situation occurs when we actually reach half of the equivalence volume. So if we measure the equivalence point volume and divide by 2, then at that halfway point between the initial point and the equivalence point, our pH will be equal to pKa. Now let's do a problem. All right, so pH, what is the pH for a titration of 25 milliliters of NH3 at 0.126 molar NH3 when 8.5 milliliters of 0.287 molar HCl have been added? We're told the Kb of NH3, right? So the first step here is we added an acid to a base. We have a neutralization step. So we have our NH3 reacting with HCl, going to products. We'll say they're NH4 and Cl minus. Now, we need to do an ICF table here. So that means we need to calculate moles of the NH3 and moles of the HCl. Now, if we do that, we get 0.00315 moles of NH3 and 0.00244 moles of HCl. Now, HCl is my limiting reactant. We also have 0 moles of NH4+. This is different from the strong acid, strong base titration, where we didn't care about the products. This case, we don't care about Cl minus. We definitely care about the NH4+ because it's a weak acid, and it's going to affect pH. So I'm going to subtract off my 0.00244 here from everything since it's the limiting reactant, and I'm going to add it to my NH4+. This is going to give me 0.00244 moles of NH4+ formed, 0 moles of HCl, and 0.000711 moles of NH3. At this point, I can use the Henderson-Hasselbalch equation, right? pH is equal to pKa plus the log of A minus over HA. Now, A minus is our NH3 because it's the weak base, and NH4 plus is our HA because it's the weak acid. We need pKa though, so we need to take the log of Kb, right? Negative log of Kb here will get me pKb. There's another way to do this as well. I'm just going to do it the way I like to do it, I guess. I'm just going to take this value, take the negative log of it. That's going to get me 4.74 for my pKb. Now, we know, hopefully, or remember from the last chapter, that pKa plus pKb is equal to 14. Or pKa is equal to 14 minus pKb. If I plug this in, I get that the pKa is equal to 9.26. Just take that, plug that in there. We could have also used Ka times Kb is equal to Kw and solved for Ka this way and then taken the negative log. It really doesn't make a difference which way you get your pKa, but you need the pKa. You can't use pKb in this equation. So now I can just plug in and go, okay, hey, 9.26 plus the log of my weak base, which is 0.000711 moles, over 0.00244 moles. Remember, in Henderson-Hasselbalch, it doesn't matter. You can use concentration or moles. I'm just going to use moles. Not a big deal here. And we can hit equals on our calculator and get our final answer. So our pH ends up being 8.72. And that's our answer to this problem. So we're going to continue the other regions of this titration in the next lecture video. So if you have any questions about the first two types of calculations we might see in a weak base strong acid titration, please let me know via email or at a discussion session. Have a good day.